Okay, so I'm going to jump around. I'm going to take you on a little tour throughout the world of pure mathematics. Just little tidbits. I'm trying to convince you that there's beauty and there's stories to be told, and mathematics is not done, and there's research going on, and people are trying to figure things out, even though it seems like it's completely finished. This is the plan. So I'm going to jump around. I'm going to be asking you guys open questions. I won't tell you the answers because answers aren't important. So the important thing here is that if you have something to say or you don't understand something, you should just interrupt me. My name is Ty. I'll leave that there. And if I'm looking the other way, just say, Ty, what do you mean by that? Or something else. Okay. So, let's do some mathematics. Math is not about numbers. I do not care about numbers. I do not care about solving for x. Okay. There are 64 squares on that board. It's 8 by 8. I give you some dominoes. Dominoes are 2 by 1. Here's a question. Can you tile that entire thing with dominoes without leaving any gaps or overlaps? Some people, yeah, someone want to say how? So, I saw you nod your head, I'm sorry. Just describe how I can tile this. It's not a trick question.
Yeah, there's two squares and the number of the amount of squares is just 2.
Right, okay. So I can like tile one there, 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 one there. That takes up the first 2 rows, and then do it for the next 3, sort of thing. Right, the whole thing will get tiled by 32 of these. Right, 32. Okay, here's a question which might worry you. Okay. Let's get rid of those 2. How many squares are on the board? 62. Okay. Who here has played a musical instrument before? Some of you. So if you're ever taught, when you're playing a musical instrument, one of the most frustrating things for a teacher is when someone tries to hide behind the person they're playing with. Right? Because if you play a wrong note, you're not going to know and you won't learn. The best way to learn is to be wrong loudly. Right? So when I ask a question and you think you know an answer, say it. Because if you're wrong, you're doing way better than that person who thought they knew the answer and got it right in their head and didn't say anything. You're going to get way further, I promise you. Right, so you've got to be loud and wrong with conviction. It's the important thing here. How many squares are there on this board? 62. Oh, look at that. And you were all right. Fantastic. Okay, so how many dominoes would I need to tile that thing? So there's 62 squares. Each domino has 2 squares in it. How many tiles would I need? 30. 30, 31? Okay, 62 divided by 2 is 31. 30, that's fine. 31's better. Okay. So, we need 31 squares. Question, can you do it? Why? Okay, so there's a problem coming. What's your name?
Ryan.
Ryan, what's your name, sorry?
Marina.
Okay, so Ryan said we have an issue here because there's sort of only 7 along there. Maybe once we get to the end, we'll have to break one. But once we do this, what if we go to the end, right, and then put one like that, and then tile it across? Right. Maybe it'll still work. So if it's going to work, it's going to work with 31. No way. So since we live in a democratic society, who votes you can do it? Okay, oh, by the way, unlike in Canada where I'm from, voting's compulsory. Okay? You get a $50 fine if you don't vote, right? Okay, so, Who thinks yes? You have to vote one of the ways. You got to go out on a limb. Who thinks you can't do it? Okay. People who said you can't do it, why do you think you can't? Look at you two.
I don't know.
Well, yeah. The correct answer. Oh man. The correct answer is I wouldn't have asked it on the mystery. Of course you can't do it, otherwise I wouldn't have asked the question. So, that's not the correct answer, but that's why you guessed no. The answer is no. Answer is not important. At this point, you just got an answer, but really, the big question is, what's actually going on? Right? Like, why can't we do it? There's enough squares, there's an even number of squares. So the first thing that was pointed out is sort of satisfied. Let's try to look at it a bit more. Let's make this thing into a chessboard. Again, the black's where they should be and white's where they should be. Okay. This is a hint as to why you can't do it.
Well, if you put all it's two by one, right? So if you put them all on the outside of those, even if you do it like you said, and once you get there, you put it diagonally down, you put it vertically, then at the bottom there's still empty space. So you always have empty space.
Right. So you're saying if you go around, then here.
Then there's always
This down here.
and there's always going to be one.
Right. But what if I do that and then put one there and then keep going?
And then
Eventually, maybe. Okay, so we're getting it right track. We want to try and think as to why we can't do this thing. When I put a domino on this chessboard, what two colors does it have to cover? It has to cover black and a white. That's right. Which squares did I remove here? Two whites. Is this going to be a problem? Yeah. How many black squares are there right now on this? 32. How many white squares are there? 30. So, if I put 30, once I put 30 dominoes on, I've got two blacks left, regardless of how I put the 30 on. So there's no way I can put this on. That's it. This is an example of mathematical reasoning. Right? This is a proof as to why you can't do this. This is what people call proof of mathematics. It's a reason that is irrefutable. It doesn't matter how important you are, or how rich you are, it doesn't make me wrong, and it doesn't make you right. This is a wonderful thing about mathematics. So, that's it. Here's a question for you. So this one, I removed two whites, and that meant I couldn't do it. It didn't matter which two whites I removed, by the way. You can make the same argument. Here's a question, though. I removed one white and one black. At random. There's one white and one black. Can you always tile it? The answer is yes. That's for you to figure out why. Okay. So like I can remove this black one and that white one. I can always tile it. Doesn't matter which black or white. That's for you guys to think about. Remember, answers aren't important, because that takes the fun away. I'm going to leave that for you to think about. Let's take a jump into the world of prime numbers. I know I said mathematics isn't about numbers, but these are cool enough. Okay. Who knows what a prime is?
A prime is a number that only has one factor of itself.
Right. So something that's divisible by 1 and itself only. For example, 2, 3, 5, 7, 11, 13, 17, 19, 23. It keeps going. How many are there? How many are there? Okay. So, who thinks they stop at some point? Right? They start getting more and more spread apart. Who thinks they stop at some point? Remember, if you think that, you got to think it with conviction. Who thinks they don't stop? Okay. So if they don't stop, that must mean there are an infinite number of them. Let's come up with an argument as to why there are an infinite number of these. Here's one thing we could do. We could run a computer program and tell it to keep checking and keep finding primes. But you know what? A computer program has to actually run. So it's never going to find all of them because it hasn't been running for an infinite amount of time. It might find things with 30 billion digits. That's fine, but it's not going to prove that there are an infinite number of primes. Because we might let it run for 40 years, but how do we know that after where it's at now, there are no more primes? We have to make some sort of argument. This is where human ingenuity is far more powerful than what a computer can do. The carbon chip is infinitely superior to the silicon chip, and it always will be. Okay, so let's prove that there are an infinite number of primes. This proof was first done by Euclid, way back when. I don't know my history too good, so I can't tell you exactly when. Okay, here's how it goes. The first step is to argue that each whole number is either prime or divisible by primes. Okay? It's either prime or divisible by primes. So let's think about this. So, what does this mean? Let's prove this thing. Let's say at some point we have all the whole numbers, and then suddenly we get to a set of numbers. There's a set of numbers which are neither prime nor divisible by primes. Okay. The argument I'm about to give you will seem like witchcraft. And it's not, but it kind of is. Because this is how mathematics proofs works. You argue something and logically it makes sense, but you don't really believe it because you sort of contradict yourself. Anyway, let's see what happens. So we have a set. Let's assume there's a set of numbers which is prime, not prime, nor is it divisible by primes. So it's into positive whole numbers. There's got to be the first one. As you're walking, 1, 2, 3, maybe you hit the first one. Right, so let's hit that first one. Let's call it Bob, or A. Okay, it doesn't matter what we call it. It's the first number that's not prime, nor is it divisible by primes. Okay, I'm going to run through this argument really quick. If it's not prime, that means it's divisible by two smaller numbers that aren't 1 or itself. Right? It's not prime because it lives in here. So, it's divisible by two smaller numbers. These two smaller numbers aren't in here because this was the smallest number in there. So these two numbers are divisible by primes, or they're prime themselves. Take all the primes and make them up. Let's call them Carl and Jim. Okay? Take all the primes and make these up. Multiply them all together, you get A. But that means that A was divisible by primes. So A can't be in this set. Which means this, and then I do it again. Okay, A wasn't the smallest element. Okay? But I had to have a smallest one. And whatever the smallest one was, you better be able to run this argument again. So this set can't have a smallest element. Which means this set can't exist. Right? Witchcraft. Okay, so every number is prime or divisible by primes. Okay, second part is the greatest proof in mathematical history. Not quite, but it's pretty awesome. Okay, what was your name? Aiden? Okay, Aiden comes to me and he says, Ty, I found all the primes, all 5 of them. Okay? And I'm like, Aiden, come on, mate. Alright. So, okay, here's what I do. I say, but you missed one. And here's how I know you missed one. I take all of these numbers and I multiply them together. Whatever the numbers are, whatever the primes are, maybe they're 2, 3, 7, 13, and 19. That was 5, good. I multiply them all together, and I add 1 to that number. And I get this number here. This number is 1 more than a multiple of this. Okay? It's 1 more than a multiple of this. It's 1 more than a multiple of this. 1 more than a multiple of all of these. So, this number is not divisible by any of these. If it's prime, you missed one. If it's not prime, well, it better be divisible by primes. It's not divisible by any of these. You missed one. Ada goes away, comes back with 20. It's like, I found them all now, for sure. What do? Same thing. Take the 20 numbers, multiply them together, add 1. It's either prime or it's divisible by primes. If it's prime, you missed one. If it's not, it's divisible by primes. Not divisible by any of these, you missed one. You can never come to me with a finite set of primes. So there has to be an infinite number. This is mathematical proof. I know I went through it quickly. So this is what mathematics is about. It's coming up with clever, beautiful arguments that sort of prove something beyond any doubt. It's not like arguing in court. Right? This is an actual argument, as opposed to twisting facts the way you want to see it. Why do we care? Right? This has to be a question you guys ask. Because I know I did, and I know most high school teachers hate this question. Right? Why do we care? To me, we care for the same reason people paint, we care for the same reason people play music, we care for the same reason people climb Mount Everest. We don't care that it's useful or practical, we care that it's awesome. This is why people do mathematics. Well, this is why people like me do mathematics. Some people do it to build bridges and things, which is useful and good and all that, but I'm not here for that. You guys know that already. Okay, let's move on to the bridges of Königsberg. And this is going to lead to your second one. By the way, those sheets in front of you, they have some problems on them. They're just to remind you about things I said. You can look at it now, whatever. Doesn't really matter. Okay, that is black water. And this is some land. Here's the blue. Königsberg was a town. 1700s, I'm not sure exactly where. It had this geographical formation with bridges. That's an island. Land, water. Question. Can you cross all 7 bridges without crossing one twice? So this is the time where I get to stand here and watch you all go. Who reckons I've got it? You think you got it?
It's not possible.
Okay, do you know why? Have you seen it before?
Pardon?
Have you seen it before?
No.
Okay. 1 second. It's one of the problems on the sheets. I don't want to spoil it for everyone. But we'll talk about it. Oh, you don't have a sheet? There's one here. It's okay, you won't need it now. You can come get it later. Okay. So, answer is you can't do it. Because this is the way I ask questions. Right? They're always stupidly misleading. I'm going to give you guys a hint and then you can think about it. 4 pieces of land. It doesn't matter what I do on each piece of land, right? Like that's irrelevant to the problem, really. So, let's rewrite this picture as follows. You've got the picture in front of you. So, I'm going to erase this. Four pieces of land, 7 bridges, 5, 3, 3, 3. That's your hint. You can think about it. Try and work out how you can't do, why you can't do it. So try and work out. If you're bored for the rest of the talk, play around with it. See what you can work out. Okay. This problem was solved in the 1700s by a man named Leonard Rockway. Probably one of the greatest mathematicians of all time. He's my office mate's favorite, because we have favorite mathematicians. This is how we roll. Okay. He laid the foundations for something called topology. Topology is the area I study, that I do research in. What is topology? It's like geometry, except you get rid of all notions of angle and distance. Which is kind of counterintuitive if you haven't done it in geometry, because that's all you really care about. But what we care about is sort of how things are connected. And this is sort of, this problem is how are these bridges connecting the pieces of land? It doesn't matter that there's water underneath them, it doesn't matter how long the bridges are, really, to this problem. So, this leads us to topology. And I'm going to rattle off some consequences extremely quickly of topology. You guys can work this out again. Okay. Fixed point theorem. This is something that comes out of topology. I will not prove any of these to you. I will just try to impress you. 2 identical pieces of paper. I take one of them. I'm going to need that later. Okay, I do whatever I want to it, as long as I don't tear it. And I put it back on top of this piece of paper, as long as it's within a piece of paper. I can guarantee you, without checking, that there's at least one point which is exactly above where it used to be when it was flat. So one point which hasn't moved vertically. Well, it might move vertically, but it hasn't moved horizontally. And it doesn't matter where I put this on here or how I scrunch it up. There has to be one point which never moved. This is a consequence of something called the fixed point theorem in topology. It's not that impressive. Here's a better thing. I take a map of Ontario and I put it down wherever I want. There has to be exactly one point which is exactly above its actual spot on Earth. It doesn't matter where I put it. It doesn't matter how I rotate it. It doesn't matter where I put it. Same reason we care about Mount Everest. Same reason we care about painting and music. We care because it's awesome. We don't care that it's useful. Right? I don't anyway, something. Okay. Antipodal fixed point theorem. It tells you the following. At any point on Earth, at any time on Earth, there have to be 2 points which are opposite each other, exactly if Earth was a sphere. 2 points opposite each other, which have the same temperature and pressure. At all times, it has to be at least 2 points where this is true. You can prove this mathematically. Pretty cool. Why is it useful? It's not really. It's kind of interesting. Okay. Something that came out of topology is something called the Poincaré conjecture. The Poincaré conjecture, I'm not going to explain it too much. If you remember to ask me about it later, during question time I will. Is worth $1 million. Because some rich guy decided to donate a whole bunch of money to research in mathematics, and in 2000, 7 problems were decided upon, and it was said that each of these is worth $1 million. Since 2000, one of these has been solved. This is called the Poincaré conjecture. It's a problem in topology, solved in 2003 by a man named Grigory Perelman, who's a Russian mathematician. He declined the money. He declined the Fields Medal, which is the Nobel Prize in Mathematics, essentially. And he completely receded from mathematics after that. So, he had his reasons, but there's a little interesting tidbit. $1 million, it's a lot of money, clearly not enough for him. Okay, here's a problem. Another problem for you. 2 potatoes. Right, they can have as many lumps as they want, just don't put any holes in them. 2 potatoes. I take a marker, I take a Sharpie, and I draw a circle on one of them. And I draw a circle on the other one. Or a closed loop, it's not necessarily a circle, just some sort of closed loop that meets up with itself, it doesn't cross itself. The question is, can you always draw 2 closed loops which are exactly the same? And what I mean by exactly the same are, if the potatoes vanish and the loops are left there, I could move one into the other without any deformations. That's what I mean by exactly the same. So 2 potatoes, can I always draw 2 loops that are exactly the same, regardless of what the potatoes are? The answer is yes. Try and figure out why. You can do it with a tiny bit of imagination. It's all it takes, and extreme amounts of ingenuity. Okay. This leads me to knots and tangles. We are doing pretty good. Okay. Here is a tangle. Here's how we make them. I'm in a field, a big field, and I put 4 stakes in the ground. Between the front 2, I tie a rope. Between the back 2, I tie a rope. Now, I'm allowed to do one of 2 things to it. I'm allowed a twist, which does the following. So a twist, you take the 2 stakes on the right, you take the front one over the back one. Let's do another twist. Okay, you take the front one over the back one on the right. Or I can turn. So these are twists. Or I can turn. So a turn is you take this whole thing and you rotate it 90 degrees. Alright, let's see if I can actually draw this. Did I do that right? Yeah, that's okay. Okay, so that's a turn. I'm only allowed to do two things. A twist and a turn. And, for the sake of this talk, we're going to call this 0. And every time we do a twist, we're going to add 1. And every time we do a turn, we're going to flip the number, so take its inverse, and put a negative sign in front of it. So what does this become? Negative. Yep, so flip the number, so 1/2, put a negative in front of it. Negative half. Okay, so those are the only rules. Pretty simple. And you keep doing this. And you keep doing this, and you keep track of the number, and you sort of have that. This tangle is 3/4, or this tangle is 7/5. So one question might be, given two tangles which have the same number, can you wiggle one into the other? Is there a reason we chose these rules? Or is there something actually going on underneath? And there probably is. So, the only way to find out is to do what any good scientist would do. Just run an experiment. I need a volunteer. I need a volunteer. Please come up. Very brave of you. Okay, I need 4 more volunteers. Yeah, we'll do it. Actually, we might do it then. Yeah, 1, 2, 3, 4. Okay. Okay. So. Take this. Alright, you're the tallest. Stand in the middle. Okay, so the 4 of you on the outside are going to be the stakes. We're going to tie you up. Alright. What's your name? Great. Okay, it was nice knowing you. Alright. Alright, so we need 4 stands. Stand there, and someone else stands here. Alright. So sort of pick up the slack a little bit. And as we tie him up, you'll have to let it go a little bit, just so he doesn't die. Yeah, okay. Cool. Over here, and so you guys the same at the back? Excellent. It's going to be brilliant. Okay. Who thinks they're pretty handy with fractions? That's it. Yeah, I never get a response to that. Alright, Josh, I'm going to put you on the spot. Mr. Ends. Yeah. Come on up. Alright. Here you go. Don't worry, it won't be all your fault. Screw up. That's right. If Josh screws up, it's your fault. You got to watch him. Okay. Excellent. So what's going to happen? What's going to happen is we're going to start at the back, and we're just going to sort of snake forward, and you're going to yell out twist or turn. And we're going to try and get the number of the tangle. The tangle's currently at 0. So, yeah, so we'll start at 0. That's right. And we're just going to keep track of the fraction as it goes here. When you say a twist or a turn, you guys do the appropriate thing. So remember, twist is 2 people on the right, front person goes over the back person, so you'll have to step over the screen. Hands down by your side, otherwise you won't be able to get out. Alright? Okay. And we're going to aim to wrap them up about here. This has ended badly before, I don't want it to end badly again. Okay. So hands straight down. Yeah, so twist is this, turn is all of you rotate one spot. This way. Okay, and Mr. Ants is going to keep track of the fraction as we go. And we're going to keep an eye on it. Okay, so let's start right at the back corner. Twist. So you go over. Yep, you go on. Yep, that's right. Excellent. Okay, our aim is to time up as badly as possible, and while we're doing it, we may as well just get that number as ugly as possible. Next. Turn. Turn. So we're at -1.
Twist.
Twist. No, so twist is, it's still whoever's on the right here. It's still whoever's here. Yeah. You go over. So the front person goes over? That's right. Oh, we're back to 0. That's boring. Get inside here. Alright, next. Turn. Alright, have a turn. What happened?
Nothing.
We're at infinity. We're at -infinity right now, which is kind of useless, but that's okay. Next. Turn. Alright, so we're back to 0. Yeah. So something divided by 0 is infinity for this case. It's just a symbol. We don't really have any meaning for it.
Twist.
Alright, next. Turn. Again.
What?
Alright, next. Twist. Alright, twist. So you go over here. Switch places. Okay, what's infinity plus 1? Infinity. Infinity, so nothing happened. Okay, cool. Next. Turn. Alright, so you're still not going to fall. Take it easy. Alright. Next. Let's do a twist. Did you say twist? I think you said twist. Okay, twist. Yep, good. Nice. Alright, remember around his, kind of his forearm area. Yeah, not that low. Yeah, okay. Twist. Another twist. So you're going over? That's right. Awesome. Next.
Twist.
Twist. Alright, what's our number at? 3. That's looking a little better. It's not 0 anyway. Yep. Turn. Okay. So what are we? -1/3. Okay. Twist. You go over. Front person goes over. Hang on, we have to add 1. Oh no, you can't see it. Yeah, beautiful. 2/3. Alright. Okay, next. That's you next to the cameraman. What a cameraman. What do you got?
Twist.
Twist. You go. No. Well.
Other way.
Alright, Hill.
Twist.
Twist. This doesn't look like we're tying them up.
Turn them.
Turn.
Turn.
Now twist.
Twist.
Twist. Cool, that's good. Hang on. Where we at?
Twist.
Someone help me out?
Twist. Turn.
5. We got a 5 from the crowd. Trust him. Alright. Next.
Oh, twist.
Twist. Yeah, he's got the right idea. He's got his head down. Alright. That's good. So, yeah. Alright. Next. Twist again. Okay, we're at 21 on 8. So, well, yeah. Alright. Next. Turn. -8 on 21. Alright, next. Twist. Okay, next. Turn. Yeah, you can get rid of that. I don't think we need it. You need some rope? Oh, just keep getting closer. I'll turn her around eventually, but yeah.
What was the last one?
It was a turn.
That's
So you just flip it and negate it. Okay, so We are currently at minus 21 on 13. Here's what we've got to put our heads together to do. We want to get that number back to 0, but you're not allowed to do any untwists or unturns. You can only do turns and twists. Okay, so we got to think about this as to how we can do this. Okay. No, you can't do anything opposite. Everything's the same. All we're going to do is try to get that number back to 0. And we're probably going to time up way worse on the way. Okay, who's next? I'm going to start now. Who's asleep? Alright, other side. Turn. Okay, so we're back to 13 on 21. Next turn. Twist. Okay.
Yep.
Oh, you're really making it hard for him. 34 on 21. Alright, next.
Twist.
Twist. Twist. 55 and 21. Oh man, that's not getting closer to, well, it might be getting closer to 0. It doesn't look like it is. Alright, next. What's the plan? Twist or turn? Did you say turn? I think you said turn.
Twist.
Okay, he's insisting on a twist. Well, let's turn. Okay. Alright, I want you to take 180 degrees, just give it a bit more. Okay, cool. That's okay. Whoa. Yeah. Okay, minus 21 on 55. Next. Alright, your turn. Yeah, we're skipping that row. Turn. Okay, hang on 1 sec. Just before we do that, so we went from 55 on 21 to minus 21 on 55. If we turn again, what happens?
Nothing.
We go back to where we started, right? So 2 turns takes you back to where you started. So, you might not want to do a turn after a turn. What do you want to do? Twist. Alright. Twist. Cool. Hang on, wait for it. Alright, 34 and 55. Turn. Cool. Yeah, you just keep following it. Alright. So we are at minus 55 on 34. Notice how the denominator got smaller there. That's what we're after. Because as the denominator gets smaller, we're going to be more likely to get to 0. Okay, next. So hang on, we just did a turn. So what happens when we do 2 turns in a row? Okay. So have a twist. Twist. No. Aiden goes over. We go. Alright, we're at minus 21 on 34. Sorry, I'm coughing. Next. Twist. Excellent. Alright. Twist. Okay, we're at third. Whoa, I don't like that. So we're at minus 21 and 34. We had one.
We're adding.
We are adding. Yeah. Sorry, that was the twist. Okay, that's looking good. 13 on 34. Let's get that 13 to the bottom next. Turn? Yes. She said turn, right? Yeah, okay. There's a turn. How you feeling? Blood circulation's pretty good? Yeah, okay. Excellent. Alright, next. Twist. Alright, so add 1. Okay, next. Twist. Twist. Sorry, we just have short time. So let's have a look at what. So we did have a twist just then. So there was a twist just then. Hang on. numbers, when you add, you only go up, right? So if you're gonna get close to 0, what you want to try and do is flip it to get negative, and then add, and then flip it, and add, and flip it, and add, and flip it, and add. So every time you get positive, we flip it. Then you add, and then you flip it, and you'll notice the denominator gets smaller. So we're currently negative. We don't want to get negative unless we don't want to turn unless we're going negative, because then we can add some more. Right? So, what are we going to do? We're going to twist? I think we're going to twist. So we twist and we add 1 to that. So let's have a look at what's happening in the number. We're at 8, minus 8 on 13. Now we're at 5 on 13. Right, minus 8 plus 1. Well, minus 8 on 13 plus 1. 5 on 13. Now let's get that 5 at the bottom. Turn. Alright. Alright, next. Sorry, there's a negative. Alright, next. Let's see. Yeah. Twist. Good choice. Minus 8 on 3. Next. Twist. This is looking good. Minus 3 on 5. Next. Twist. Alright. 2 on 5. What do we want to do next? Turn. Oh, this is looking good. Minus 5 on 2. Twist. Minus 3 on 2. Next. Twist. Minus a half. Next. Twist. Okay, we're going to take U4. Sorry. I'm going to get these guys both. Alright, what do you want to do? We're at a half. Turn. Alright. So we're at minus 2. What do we want to do to get to 0? We're at minus 2. Two twists. Alright. That's not a twist.
That's a turn.
1, 2. Okay, hold on to your ends, do not let go. We're at 0 now. He's pretty tied up. Damn. Alright, do you reckon you can get yourself out? Do not let go of the ends. No? No luck?
Oh, yeah.
Oh, okay, yeah. Wait. Hold on to your ends. Do not let go of your ends. Alright, hold on. Hold on. No, that's fine, you can let it go. Okay, have a pull, just wiggle it a little bit. Wiggle it a little bit. Oh my god. So we're at 0. Give it a wiggle. Give it a wiggle. I'm not convinced it's helping. Oh! Alright. Excellent. Let's have a round of applause for our volunteers. So that's a cool little trick. Where's my piece of paper? It's from So that's all I have for you. Thank you. And if you have any questions, just like a couple of yeah. I'm happy to answer questions about anything, not just about math. We got like 10 minutes or so. So yeah, fire away, whatever you want to know. Or I can just tell you another story. Yeah.
Wait, where are you from?
I'm from Australia.
Oh, okay.
Yeah, voting's compulsory. I should learn this. Yeah. So something I forgot to mention about these prizes. Prizes like, if the math didn't get you excited, $1 million has to, right? So, this award he turned down, he also turned down the Fields Medal. The Fields Medal is this Nobel Prize in Mathematics. It's awarded 4 times every 4 years, so once a year essentially. This year, there was one of these meetings. It's called the International Congress of Mathematicians. It was held in Seoul. This year we had the first Canadian Fields Medalist. So So this is like the most prestigious prize you can get in mathematics, essentially. First Canadian fields medalist, his name was Mennonite. First South American fields medalist. First Iranian fields medalist. But more important than any of these was that we had the first female fields medalist. Which means that about 3,000 years too late, the people in charge of deciding this award, it hasn't been going for that long, have finally realized that there's no difference between the genders. There are still some people in mathematics, right at the top, who believe that mathematics is a men's game. Their time has passed. There is overwhelming evidence to suggest this is not true. There is no reason whatsoever, besides maybe society telling you so, that females are not as good at mathematics as guys. I don't know why this has been the case, but it has. These people at the top of the game, they're going to die soon. Their time has passed, they don't know it. Yeah, there's plenty of excellent female mathematicians and they're becoming more and more prolific. Her name is Mariam Mirzakhani. Fantastic, incredible mathematician. Yeah, the Canadian's name is Mela Bhargava. If you're interested in this stuff, it has a fascinating history. The medal was actually founded after a Canadian. And this was the first year since 1900 when it was first awarded that a Canadian's medal. So that's something to be proud of. Yeah, something I forgot to say. You should know these things.
Questions for Ty about what you heard, or maybe about what he does for his work, or anything else?
Yeah.
Yeah, how can your field of mathematics be applied to
So, I have plenty of friends who graduated from PhDs. Well, I have at least. Most of my friends who graduated either went into academia, which is fine, but that's probably not what you're asking. A lot of the skills, so the stuff I do might be applied. I don't know. Maybe 200 years down the track. I don't really have any idea. So this has happened throughout history over and over again, where the geometric framework for general relativity, which is Einstein's theories in the early 1900s, was laid down about 40 years before he was on the scene. Laid down for its own interest, for its own sake, its knowledge for its own sake, and then it was applied later. In terms of directly getting a job with the skills I learned that make me employable are not the mathematics, it's the ability to solve really hard problems. So when you train as a mathematician or a physicist or these kind of jobs, or these kind of degrees or training, you're very desirable to banks and you're very desirable to spy agencies, like the Canadian government. I have a friend who graduated for a PhD in pure mathematics and number theory. He currently works for CSIS. I think I got that right, I don't know. In Ottawa. I don't know what he does, he's not allowed to tell me. But these are the people you want cracking codes. Guaranteed. Because they're going to do it better than anyone else. So I guess that's the best answer I can give you in terms of application. Yeah. I mean, no one really asks a musician or a painter that question. This is kind of the message I want to get across today. No one ever asks that, like, you can play the sax pretty well, but come on, really? Like, no. Yeah.
When did you figure out that you loved math and was abstract pure math?
Yeah, so I went to, in end of 2000 and, no, beginning of 2007, in January, I went to this maths camp. It's awesome. That's where I learned how to cube. And that was a 2-week program where there were no assessments, there was no competition. It was just sort of, here's a little bit of a push, some basic stuff. Go figure out what you can do with it. There's some problem sheets to guide you along. It's much easier to do in an idealized place like that where there's no curriculum, obviously. But that was, I did a course on knot theory. So knot theory is like asking this question. Are these two knots the same? And what I mean by that is, can I wiggle one into the other? Okay? And these questions are, you look at that and you go, no freaking way can I. Okay? But questions that are obvious are usually the hardest to prove. So we did a whole course on this stuff. I did a course on number theory, one on game theory, and this was just fantastic. It was so beautiful. This aesthetic value of mathematics was something that I never ever saw before I went to this place. And it was right at the end of high school, unfortunately. Our curriculum doesn't let us, which is really unfortunate. But it's up, if you want to see it, it's really up to you guys, because there's plenty everywhere. You just got to open up your eyes and look around, and read some books, ask your teachers. If they don't know, that's fine, you can learn it together. Yeah. 2007. And then I couldn't really do anything else. Any other questions?
All right, let's thank Ty very much for his time this morning. And